Okay, now based on the three cases we learned before. Okay, the first one is normal case, right? Normal case. The system can be either stable if there's no sign change on the first column, right? Or if there is sign change, at least one sign change, the system is unstable. Okay, that's normal case. For special case 1, the system can be only unstable. There's no, if you fill up the table and then you found that one of the first row is 0 and followed by non-zero, the system is unstable. Okay, remember that you need to replace that with epsilon, and then replace the epsilon with small positive or negative number, so the system will become unstable. For special case 2, where the entire row is 0, right? So the system can be solving that, can be marginally stable or unstable. Okay, so we will demonstrate this after this. Okay, this is the cases that we will find when we fill up the RH table. Then based on the RH criterion, we can determine whether or not the system is stable, not stable, and so on based on this, right? I would like to go through a few examples on top of the example that we have in the notes in the slide. So for normal case, let's try this simple so that you can actually guess, the system itself is stable without actually having to solve these RH array. All right, so this is our common example here, right? So the system is stable, you know that, because if we solve this denominator, we got s equal to -1, s equal to -2, right? So plotting this on the s-plane, the system is stable, right? But right now, we using the transfer function that is stable, we need to solve this using RH. We need to verify whether the RH will tell us the same stability or not, right? So from here we can actually start from S0, right? Okay, now fill up this 1, 3, 2. So we know that there's nothing wrong with this. We have a real numbers here. So we need to find the next one here, right? Which is 3 times 2 minus 1 times 0. So which is 3 times 2 minus 1, 0 divided by 3. So that's what the value is here. So we're getting this 3 minus 0, 6. So it's actually 2, right? So that's actually the value, that's 2. So 2, okay, let me draw again. 3, 2, 1. So we have basically 1, 3, 2. Okay, 2. So we need to see this, the first column, right? What is the signs? So we have a positive here, this positive 3, positive 2. So from here to here, is there any sign change? No. From here to here, no sign change. So if there's no sign change, that means the systems, all the roots are no sign change. No. Means all the roots are on left half plane, right? So how many? So we need to look at this. No, this is, sorry, this is 0, 1, 2. Sorry, yeah, sorry. 2, 1, 0. Okay, that's so how many poles that we have? How many roots we have? 2 because of this 2, right? So 2 on the left hand plane. Okay, All right, that's the first example. Okay, that's the first example we have. Let's do the second one with our non-example, right? So that's our second g of s equal to 1 s squared minus s minus 6. Okay, so we know that factoring this, we got s plus 2 and s minus 3. So this part here, the system is not stable, right? This one is s minus plus 3. This one is s minus 2, s plus minus 2. So this one will be on the right hand plane. The system is definitely unstable. But right now we need to verify with RH array, RH criterion, whether the systems tells the same story or not, right? So this is 1 as 0. Okay, we have 1 here, minus 1 here, minus 6, right? So we have negatives here. Fill out this one. This one will be minus 1 multiply minus 6 minus 0 divided by minus 1. So actually the values here is minus plus 6 divided minus 1 minus 6, right? So that's actually minus 6. Okay, so if we plot it again as 0, so we have here 1 minus 1 minus 6. Okay, so this is plus minus minus. Plus to minus, there's one sign change. Minus to minus, no sign change. That means one sign change. We have one roots on right hand plane. And then one root, of course, will be on left hand plane. That's how it goes. Total root would be 2. Total number of roots are 2. So we can verify this. If let's say we have a complex problems, we can verify using this to tell whether or not the system is stable, and then how many roots on the left hand plane, right hand plane, and etc. Right? So now we just prove that with the simple uh, systems, we could actually verify the systems whether is it stable or not stable. Okay, that solves the problem for case, especially normal case, right? Okay, now in normal case, it tells us whether the system is stable or not stable depending on the sign change on the first row. Okay, now we want to see what is the for special case 1, right? For special case 1, if let's say we have example like 0s2 plus 2s plus 6. Okay, so this part has zeros, that means, but this is for the second order, right? So we know that these systems is stable or not stable by finding the roots here. We can find it, right? So it turns out, let's say if I use the MATLAB, okay, I use MATLAB here. You can use as okay, as okay, gs equal to 1 over let's say as 3 plus 2 s plus 6. All right, so that's exactly what is our systems. Then we can run p zmat, right, equal to p zmat g of s gs. Okay, then we can see that there are two roots, right? Two roots here. the first and the second ones are on the right hand planes, right? We know that the system is unstable, right? So one is on the left, two on the right. Okay, now let's put this one aside. Okay, so we need to verify this. Okay, we need to verify this. We have to verify this using RH array. So we can have add straight power 2 S1 S0. Okay, S1 0 2 6. Okay, fair enough. So you see here, this condition, as it tells us, this condition, without further calculate the rest of the column, it tells us the system has 0 here. Because we don't solve the 0 here, okay, so now if this, when we fill up this, we already have 0 here. If we don't solve this 0 here, we can't solve this one, the remaining, right? So it becomes infinity here. So we need to solve this. We need to replace this by replacing this epsilons there. So now the system itself is already special case 1. Okay, so the rest we need to fill out this is, let's say this is A1, B1, A2, B2. So let's calculate A1 is A1 equal to epsilon 2 minus 6 times 1 divided by epsilon. So that is A1. So basically 2 epsilons minus 6 over epsilon, right? So A2 definitely is 0. A2 definitely is 0, right? Because this one multiplied by 0. Okay, B2 equal to A1, which is this one, minus 6 divided by A1, which is this one, right? So now let's epsilon equal to small positive number, right? So 0, maybe 0 0.001, so if it is small positive number, it becomes positive, right? So this is positive epsilon, right? So this one, A1 here, how to solve it? This is positive, small number multiplied by 2. So it don't change much because so it's become a small number there, minus 6 divided by positive number. So you got this negative, right? So that part here, the sign is negative. We can calculate this value, but we're interested to know the signs. There's negative there. So once A1 is negative, this is negative small number, minus 6 becomes negative 6 plus something, divide by A1 is also negative, okay, negative, positive. So that becomes positive, right? So now we have that the first row here. Need to see is there any sign change or not. That's positive to positive, no sign change. Positive to negative, one sign change. Negative to positive, two sign change, right? Two sign changes. So that means in this case we have two sign change, right? So that means two roots on right hand plane, which is, that means there are two roots on this side, two roots, right, on this side. So the system is definitely unstable, and then one more root is on the somewhere this side, right? So we have two roots there, and then it is tally with the MATLAB calculations, MATLABs. You see that there are two roots, imaginary roots on the right hand planes, and then there's one root on the left hand plane. Hence the system is unstable, right? So and then it's the special case 1 is always unstable, so it is true. So that's example number 2. Let's move on to special case 2 quickly. Special case 2, we have simple ones. Let's say we need to do um, um, an example that we know the system is stable or not stable, not stable. So right now we have a system like this, right? S minus 1. So looking at this, we know the system is not stable, right? But this one here, so we'll have a systems. Um, this one is on imaginary, okay? This one is on the right hand plane. So if we use MATLAB, we use GS1 special case to equal to 1 over. You need to multiply this first, okay? So 1s cubed s squared plus 9s plus minus 9. Okay, then we can fill up this s to the power of 3 minus s to the power of 2 plus 9 multiplied by s minus 9. Right, so we have that. And running a PZ we run PZ map straight away. Okay, running a PZ maps for CS1 system. Then we have, you see that there are 1 poles here. There's a 3 on the imaginary axis, right? 3, this one, yeah. So there are 2 on the imaginary axis. So we know the system is unstable with 2 on the imaginary axis, right? Alright, now we need to verify the systems, whether the system is, the RH criterion is telling us the same story. So there's 1 minus 1, 9 minus 9, right? Okay, now solving this, we know that this becomes, okay, there's 0, 0. So this actually fulfills special case 2, right? Special case 2, because the entire row is 0, right? So we cannot move further by replacing epsilon and so on. So we need to go back to the previous equation line so we can find the auxiliary equations. Auxiliary equation, which is in this case minus 1 s squared minus 9. Okay, so s squared minus 9. So dps of this is our ps. ds, we have 2s, right? That's 2s. Take this equation, put it here. So we have 2 there, 0 is okay there. So that's 2 because only this component, right? This s1 component. Put it here, 2. So this, the rest is minus 2 minus 9 minus 0 divided by 2. So we have this one, we have 18th, 9. So we have minus 9, right? Minus 9. So from here, you see that the first one, because of this one, right? We know that their system has some poles on the imaginary axis. How many poles, how many roots, depending on the auxiliary equation, the order of auxiliary equations. So now in this case, the order of auxiliary equations, we have 2. So there's 2 poles on the imaginary axis. Okay, so we have 2 roots on imaginary axis, right? 2 roots because of this. Okay, and then because the system itself has third order systems, 1 more root depends on the, is there any sign change or not. Okay, positive 1, yeah, there's a sign change, right? Okay, because we already have a sign change there, because the total we have a third order system, right? So that means we have one root on left hand plane. Okay, if there's no sign change here, okay, mm, even though you see that there's a plus minus here, right? Positive minus, and then you go positive back. So we can't say that there are two, because two sign change, we have two roots. So because we need to count that when we have the system change, because there's the total of roots are three. So two roots on the imaginary axis already, one roots on the left hand plane, and then it is perfectly tally with the systems, the MATLAB's answer here, right? So we have two roots on the imaginary axis, one on the right hand plane. So that tells us basically the system is stable, not stable. If we have complex higher order systems, then we can use this one to check whether or not how many poles on the right hand plane, left hand planes, and the imaginary axis, right? So this is very important criteria for us to determine whether or not the system is stable after this, right? We normally use the criteria for special case 2 because we we need to be we need to be able to determine when the system become unstable. Okay, never mind. All right. Right now, hopefully you understand special case 1, special case 2, and normal case. All right. Thank you.